The tablet, designated BM45728, sits in a climate-controlled drawer at the British Museum, its clay surface pressed with cuneiform marks no wider than a fingernail. Scholars who read it found that the Babylonian scribes who carved it, inheritors of a Sumerian astronomical tradition, reaching back across millennia, had calculated the moon's distance from Earth with an error margin of less than 2% compared to what our instruments measure today. That tablet is roughly 25 centuries old. What observation, what accumulated record, what chain of patient watchers would have been required to arrive there? Tonight we follow three traces left within that ancient record: the mathematical tablets pressed in clay, the architectural alignments cut into stone across Mesopotamia, and the data returned from the lunar surface itself, to ask not what we can conclusively prove, but what the evidence quietly suggests when we hold it without urgency. We'll move through the cuneiform archives, the lost Sumerian records, and a set of open questions that modern instruments have perhaps unexpectedly made harder to close. The Sumerian sky was not a backdrop. It was an archive. At Ur, beneath the great ziggurat built around 2,100 BC priests, recorded the moon's path with a consistency that spanned not years, but centuries. The cuneiform tablets they left behind and the tens of thousands catalogued across Babylon, Nippur and Sippar preserve what modern archaeo-astronomers have since verified through computer modelling. A Saros cycle, calculated to within minutes of modern measurement eclipse, timings predicted decades in advance, and lunar position calculations employing mathematical sequences that European scholars would not formally develop until the 17th century. What is unusual is not the knowledge itself. Ancient civilizations across the world observed the sky carefully. What is unusual is the institutional continuity, the sense embedded in these texts of a record-keeping apparatus that did not pause, did not begin again from zero, but accumulated, refined and transmitted across dozens of generations with a precision that does not yet have a comfortable category in our standard histories. The light in those temple chambers would have been small. Oil lamps, moving shadows across clay already marked with notations that would take modern specialists years to decode, and the silence would have been deliberate. These were not casual observers. The colophons on tablet after tablet identify individual scribes, their lineage, their teachers, the texts they copied, and the calculations they corrected. There is a texture to these archives that feels less like mythology and more like maintenance. Consider one detail in particular: the ephemeris tables from the Seleucid period, inscribed between roughly the 7th and 1st centuries BC, calculate lunar positions up to 600 years into the future with an accuracy margin of less than 10 arc minutes. To reach that, the scribes working on those tablets needed to account for three separate gravitational inequalities affecting the moon's orbit: the elliptic inequality caused by its elliptical path, the evection introduced by solar perturbation, and the variation caused by changes in the sun's apparent motion through the year. The procedures they used were not rediscovered in Western astronomy until Kepler and not fully explained until Newton. They tracked all three apparently without telescopes, without our mathematics, without any of the tools we would assume necessary. That alone is worth sitting with. But the questions that draw us deeper tonight are not only mathematical. Running alongside these astronomical archives is a second record older stranger, and often far more difficult to interpret. The cuneiform texts of ancient Mesopotamia describe a hierarchy of beings called the Anunnaki, and among their functions they are associated repeatedly with the moon. The lunar deity Nana, whose great ziggurat at Ur was oriented to the cardinal directions with less than 1 degree of error, is described in hymns and administrative texts not merely as a symbol but as an occupant. His celestial dwelling is referred to with Sumerian terminology that translates literally as Great House of Heaven. The texts describe him travelling between his earthly temples and this abode following the lunar orbital path, disappearing from terrestrial view during the 3 dark days of each new moon. Whether this represents cosmological metaphor, encoded astronomy, or something else entirely, the texts themselves do not tell us clearly, and that ambiguity is part of what makes this record worth following slowly. Then there is a third layer, quieter still. Beginning with the Apollo missions and continuing through Lunar Prospector Clementine, and the Lunar Reconnaissance Orbiter scientific instruments have returned data from the lunar surface that carries its own set of open questions. Gravitational anomalies, mascons whose distribution affects orbital mechanics in ways that ancient eclipse calculations may have had to account for. Acoustic signatures from moonquakes that suggest internal structural complexities larger than conventional models predicted. Water ice confirmed in permanently shadowed craters near the lunar South Pole regions that Sumerian hymns to Nana describe as surrounding the moon god's dwelling with waters that never see the sun's face. These convergences may be coincidence. They may reflect the human tendency to find patterns that confirm what we already half believe, or they may suggest that some of what the ancient texts preserve is not mythology dressed in the language of astronomy, but astronomy dressed in the language available to its time, waiting patiently in clay. We will not resolve that question tonight. That is not the purpose of this kind of listening. What we will do is move through the record carefully, the mathematical tablets, the aligned stones, the lunar data, and allow the evidence to surface at its own pace. So we begin with the oldest layer, the clay, the numbers, the watchers who carved them. The three paths of the sky. In the year 1000 BC, give or take a generation, a scribe somewhere in Babylon or Assyria pressed a reed stylus into a slab of wet clay and began recording the first of what would become two tablets known today as the Mulapin. The room would have been dim, the air carrying the faint mineral smell of fresh clay, and the scribe's hands would have moved with the practiced steadiness of someone copying, not composing, but transcribing from sources already older than the institution he served. What he was pressing into that wet surface was a division of the entire night sky into three invisible roads, the way of Anu, the way of Enlil, and the way of Ea. Each road held specific constellations with assigned rising times, set intervals, and lunar passage calculations of a precision that would not become unremarkable until the development of modern celestial mechanics. What makes this detail worth holding is not the tablets themselves, but what modern astronomers have found when they run the underlying observational data through computational sky models. The astronomical records embedded in the mul.apin do not originate from around 1000 BC. They reach back to the 3rd millennium, to a period when the great cities of Sumer were still being laid out across the clay plains of southern Mesopotamia, when the ziggurat at Ur had not yet been built, when writing itself was still a relatively new technology. The tablets, in other words, were already ancient when they were copied. And the question that opens quietly inside that fact is not what the scribes knew, but who taught them, and across how many unbroken generations that new knowledge had already travelled before it was pressed once again into clay. The Saros cycle sits at the centre of what makes this record difficult to dismiss. It spans 223 lunar months, 18 years, 11 days, and approximately 8 hours, and it describes the precise interval after which the geometry of Earth's moon and sun returns to nearly the same configuration, allowing eclipse patterns to repeat with predictable regularity. The Sumerian and Babylonian astronomers not only knew this cycle, they had calculated it too within minutes of what modern instruments confirm. And that level of precision does not arrive from casual sky watching or the observation of a single careful generation. A margin of minutes across an 18-year cycle requires consistent measurement taken from fixed points recorded in standardized notation and compared across not one human lifetime but many. That is where the quiet problem begins, not in the number, but in what the number implies about the institution behind it. The mul.apin tablets preserve considerably more than the Saros cycle. They track the moon's apogee and perigee, the 2 points in its elliptical orbit where it sits farthest from and closest to Earth. They describe the moon's zodiacal path with mathematical corrections that account for what we now call orbital eccentricity, the observed fact that the moon does not travel at constant speed, but accelerates when drawing nearer to Earth and slows as it moves away. This relationship is in formal astronomical terms a consequence of Kepler's second law of planetary motion, a principle Johannes Kepler would articulate in 1609 AD. The scribes of Babylon had no name for it, no theoretical framework that would satisfy a modern physicist. They simply observed the variation with sufficient patience and consistency that it became embedded in their calculations as a matter of routine correction, and then they moved on to the next problem. The detail is small, but it refuses to go away. We are looking not at a moment of genius, but at the output of a system that somehow held across centuries without apparent interruption. At the centre of this system, woven into its mathematics and its theology in ways that cannot be fully separated, stands the figure of Nana. He appears in these texts not as decoration but as function. He is the divine timekeeper whose lunar phases, regulated agricultural calendars, the timing of legal proceedings, and the cycle of religious festivals across every major city of Mesopotamia. His iconography remains consistent across centuries of cylinder seals and temple inscriptions, and an elderly figure with a flowing beard of lapis lazuli, crowned with the crescent moon carrying a staff said to measure the passage of time. He is the son of Enlil, the lord of air and authority. He is the father of Utu, the sun god, and of Inanna, the goddess associated with Venus, and he occupies in the broader Anunnaki hierarchy described across Mesopotamian literature a role more administrative than ceremonial, the keeper of the Tablet of Destinies, the divine record of fates determined by the Celestial Council. His judicial function in these texts emerges specifically from his light. The moon god illuminates darkness, revealing what the night would otherwise conceal, and this capacity makes him in the Mesopotamian legal imagination the natural presiding presence over matters of hidden truth. Temple hymns describe his court, his deliberations, his movements between earthly shrines and a celestial abode, described in the Sumerian term Ekuren Ki, which translates as Great House of Heaven. The linguistic construction is specific to the same grammatical structure used in administrative texts to denote physical buildings, warehouses, archive chambers, not the vocabulary typically employed for abstract spiritual realms. Whether that distinction was intended literally by the scribes who wrote it, or whether it reflects a metaphorical system we are only partially equipped to read, remains genuinely open. Some scholars treat it as elevated poetry. Others argue the specificity of the language deserves more careful attention than it has traditionally received. There is one recurring detail in the text describing Nana's movements that sits with particular stillness in the record. Each lunar month during the 3 dark nights of the new moon phase, the period when the moon is geometrically positioned between Earth and Sun, and therefore invisible from the ground, the text described the god as absent, travelling to his celestial dwelling beyond the reach of terrestrial observation. 3 days of disappearance built into the theological calendar with the same regularity that the astronomers built the Saros correction into their eclipse tables. The god's absence and the astronomer's calculation occupy the same 3-night window month after month across a tradition spanning millennia. Whether that is correspondence by design or the natural consequence of a civilization that made no distinction between what we would call religion and what we would call science, is one of the questions this record keeps asking without answering. 3 roads across the sky, hundreds of tablets, 18 years and 11 days measured to within minutes by hands that pressed their knowledge into clay and trusted it to last. We follow the second path now into the stone. The stone that faces the moon. The corners of the great ziggurat at Ur are oriented to the cardinal directions with an accuracy of less than 1 degree of error. That single measurement, confirmed by modern surveying instruments applied to the surviving foundation, contains within it an enormous implication. Not because aligning a structure to north, south, east and west is itself extraordinary, but because achieving that alignment to within 1 degree across a base that spans over 60 meters on each side using only the instruments available in 2100 BC requires a methodology precise enough to demand explanation. The builders of Ur-Nammu's ziggurat were not approximating. They were solving an engineering problem with the kind of tolerance that leaves very little room for casual error. And the question the foundation quietly poses is what observational tradition, what accumulated technical knowledge stood behind the hands that placed those first stones. The ziggurat rises in 3 distinct levels, each corresponding to one of the primary phases of lunar visibility: the waxing crescent, the full moon, and the waning crescent. This is not an interpretation imposed by modern analysts looking for pattern. It appears in the architectural record through the placement of chambers on each level, each containing openings oriented to frame specific portions of the night sky at specific times in the lunar cycle. Archaeoastronomers studying the site have identified these openings as functional observation points, not decorative windows designed to isolate and track the moon's passage through particular sections of its orbital path. The uppermost platform, which once supported a shrine dedicated to Nana, provides an unobstructed sightline across the entire arc of the moon's movement from moonrise to moonset. The structure read this way is not merely a temple. It is an instrument one built from millions of fired bricks oriented by methods we have not fully reconstructed and calibrated to a celestial body whose cycles its architects had been recording for generations before the first course of brick was laid. Beneath the ziggurat excavations have uncovered a series of underground chambers connected to the structure's foundation by corridors that show evidence of deliberate construction rather than incidental storage. The floors of these chambers contain stone platforms carved with precise angular markings and shallow channels cut into the stone surface in patterns that appear designed to track the movement of shadows cast by moonlight entering through specific apertures above. The positioning and orientation of these shadow channels correspond, when measured against the lunar calendar, to a system for detecting lunar parallax, the slight apparent shift in the moon's position when observed from different points on Earth's surface. Parallax measurements of the moon allow calculation of its distance from Earth, a value that the tablet BM 45728 in the British Museum records with less than 2% error compared to modern figures. The underground chambers at Ur may represent part of the observational infrastructure that made calculations like that one possible. That is not a conclusion the evidence can fully support. It is, however, a direction the evidence keeps pointing. What makes the ziggurat at Ur more significant in context is that it does not stand alone. Across Mesopotamia at Babylon, at Nippur, at Eridu, similar structures demonstrate astronomical alignments that vary in precise and purposeful ways, as though each site was designed to serve a specialized function within a broader observational network. The ziggurat at Babylon, dedicated primarily to Marduk but containing shrines to Nana, demonstrates alignments with specific lunar standstill positions, the extreme northern and southern points of moonrise and moonset that mark the outer edges of the moon's 18.6-year nodal cycle. These standstill positions occur only twice in each nodal cycle, and detecting them requires systematic observation sustained over decades, since the moon's movement toward and away from its extreme positions is gradual enough to be invisible without careful measurements across multiple years. The fact that the Babylon ziggurat was aligned to these positions at all implies that the architects knew where those positions were before they began building, which implies in turn that someone had already been watching long enough to find them. The nodal cycle of 18.6 years sits alongside the Saros cycle of 18.11 years in a way that suggests the Babylonian astronomers understood the relationship between them. The Saros governs eclipse recurrence. The nodal cycle governs the moon's range of rising and setting positions across the horizon. Together, they describe the two primary long-term rhythms of lunar behavior, and the architectural record at both Ur and Babylon encodes both one in the underground chambers calibrated to monthly parallax measurements, the other in the orientation of the structure itself toward positions that appear only twice per generation. The detail is quiet, but it accumulates two different ziggurats in two different cities encoding two different lunar cycles, both requiring observational baselines that stretch across decades of sustained and standardized watching. Some researchers argue this reflects nothing more than sophisticated priestly tradition, inherited, refined, but ultimately local and independent. And yet the consistency across sites separated by hundreds of kilometers suggests coordination of some kind, a shared methodology that transcended the political boundaries between city-states. The mathematics embedded in the architectural proportions of these structures extends beyond astronomical alignment into what might be called sacred geometry, though. That phrase carries associations that can obscure more than it reveals. The foundation measurements of the Great Ziggurat at Babylon, when analysed, demonstrate dimensional ratios that align architectural proportions with the numerical relationships governing lunar and solar orbital periods. The height-to-base ratio of the structure corresponds to mathematical constants that appear independently in cuneiform astronomical texts, not approximately but with the kind of precision that requires deliberate calculation. Whether the architects were encoding these relationships intentionally as a form of built cosmological record, or whether the correspondence emerges from shared mathematical conventions applied independently to both astronomy and construction, remains a question the stones cannot answer on their own. What the stones can say is that whoever designed them was working in a mathematical tradition deep enough to leave traces in the geometry of the foundation itself. The ziggurat at Ur still stands or partially stands, its lower levels preserved well enough that the original brickwork remains legible, the mortar still visible between courses, laid more than 4,000 years ago. To walk along its base at night in the silence that now surrounds a ruin that once stood at the centre of a living city is to encounter the peculiar weight of a structure built not for permanence alone but for precision. The builders knew the moon would keep moving. They built accordingly. We move now from the stone into the clay to the rooms where the calculations were kept and the scribes who kept them across time in ways that raise their own quiet questions. The archive that did not forget. 50,000 cuneiform tablets have been recovered from the temple archive at Sippar alone. That number, when encountered in an academic catalogue, tends to pass quickly one large figure among many in the literature of ancient Mesopotamia, but held for a moment longer, it begins to exert a different kind of pressure. 50,000 tablets spanning more than 1,500 years of continuous astronomical observation, organised according to classification systems that cross-reference celestial events by date, by coordinate, by associated omen, and by mathematical relationship to other observations recorded elsewhere in the same collection. This was not a library in the casual sense. It was a living research infrastructure, maintained across generations, capable of retrieving specific celestial data from centuries prior with the kind of efficiency that implies not just storage but active use. And the question that detail opens is not merely how they recorded so much, but why what purpose sustained across 60 or more generations of scholar priests demanded that level of institutional commitment to the continuous documentation of the sky. The colophons on individual tablets begin to answer that question in small, precise ways. A colophon is the notation a scribe adds at the end of a tablet to identify himself. His teacher, the date of composition, and the relationship of the text to others in the same computational sequence. The Sippar tablets carry colophons that create traceable chains of mathematical development spanning centuries. One scribe copying and correcting the work of a predecessor who copied and corrected another for him, the corrections themselves documented, so that later readers could understand not only the conclusion but the refinement process that produced it. This is recognisably the structure of cumulative scientific practice, observation, recording, error, correction, transmission. The institutional framework that sustained it at Sippar operated across political disruptions, military conflicts, and dynastic changes without apparent loss of a methodological continuity. That resilience is itself a kind of evidence not of supernatural origin, but of extraordinary organisational sophistication applied to a single sustained purpose across an almost incomprehensible span of time. At the centre of what the Sippar archive preserves are the ephemeris tables, computational documents that calculate lunar positions not for the current month, but for decades and centuries into the future. The ephemeris tables from the Seleucid period, inscribed between roughly the 7th and 1st centuries BC, calculate lunar positions up to 600 years ahead, with an accuracy margin of less than 10 arc minutes. To achieve that, the scribes working on those tablets needed to account for 3 separate gravitational inequalities affecting the moon's motion: the elliptic inequality caused by the moon's elliptical orbit, the evection introduced by the sun's gravitational pull on the Earth-Moon system, and the variation caused by changes in the sun's apparent motion throughout the year. Modern celestial mechanics names these 3 effects and understands their physical causes. The Babylonian scribes name nothing and explain nothing in physical terms. They simply built correction algorithms for all 3 into their computational procedures and produced results accurate enough that later Greek and Roman astronomers encountering Babylonian ephemeris tables adopted the underlying mathematical constants without modification. The numbers were simply better than anything available in the Western tradition, until Kepler and the Greeks were pragmatic enough to use them. The computational technique embedded in the ephemeris tables is worth examining in more detail, because it is where the archive's sophistication becomes most difficult to explain away as simple accumulated observation. The Babylonian scribes modelled the moon's varying orbital speed, using what mathematicians now recognise as second-order arithmetic progressions sequences, in which the differences between successive terms themselves change at a regular rate, allowing the scribes to approximate curved variation using arithmetic tools alone. This method was not formally articulated in European mathematics until the 17th century. The Babylonian scribes did not articulate it either. They simply applied it consistently and correctly across hundreds of tablets spanning multiple centuries, suggesting that the technique had been developed, tested, standardized, and transmitted as institutional knowledge long before any of the surviving tablets were inscribed. The archive we have may be a late copy of a tradition considerably older than the clay it is currently pressed into, and that is where the quiet problem deepens. How far back does the original observation go? The Archive of Nabu Ramani. A renowned Babylonian astronomer of the 5th century BC, whose tablets have been identified among the Sipar collection, contain step-by-step computational worksheets that document not just the final ephemeris calculations but the intermediate steps, the raw observational data, the trial computations, the corrections applied when predictions failed to match subsequent observation. These worksheets are in a meaningful sense the laboratory notebooks of ancient astronomy, and they reveal a practice of systematic error analysis that adjusted prediction iteratively against incoming observation. The accuracy of the final ephemeris tables was not assumed. It was earned through a cycle of prediction, observation, comparison, and correction that looks in its basic structure like the methodology of empirical science. Some researchers find this framing anachronistic, and they are not wrong to raise the caution. But the worksheets themselves do not become less methodical for the caution. They remain what they are, documents of a community that was trying over centuries to get the numbers right. One detail from the archive sits with particular stillness. Among the Sipar tablets are documents that claim to preserve astronomical data from the reign of Sargon of Akkad, who ruled in the 24th century BC, a period more than 1,000 years before the tablets currently housing that data were inscribed. The mathematical consistency of those early records with later observations suggests either extraordinary accuracy in ancient chronological systems or access to an observational tradition that extends further back than any physical archive we have yet recovered. The temporal reach implied by that claim exceeds the conventional chronology of Mesopotamian civilization as we currently understand it does, and most scholars treat the attribution with appropriate skepticism. The detail is small, but it refuses to go away, not as proof of anything, but as a marker of how much the archive may contain that we have not yet found. 50,000 tablets, 1,500 years of documented observation, and behind those a tradition that the tablets themselves insist is older still. We turn now toward the mathematics that made the archive possible, toward the numerical system built, it seems not by accident but by design, the system built for the sky. 60 is a number that does not arise naturally from the human hand. 10 as we count on fingers and base. 10 follows from that simple biological fact, with an inevitability that makes it feel less like a choice than a discovery. 60 requires something else. It requires the recognition that a single number can be evenly divided by 2, 3, 4, 5, 6, 10, 12, 15, 20, and 30 simultaneously, a property that makes it for the purposes of calculation is involving fraction cycles and angular measurement, one of the most computationally efficient bases available to a mathematician working without more mechanical aids. The Sumerians chose 60, or more precisely, the mathematical tradition that the Sumerians inherited and the Babylonians refined was built around 60 in a way so thoroughgoing, so systematically applied across astronomy, architecture, commerce, and law, that the question of whether it was chosen or received begins to press quietly against the record. We still divide the hour into 60 minutes and the minute into 60 seconds. We still divide the circle into 360 degrees. The Sumerian sexagesimal system did not merely influence our mathematical inheritance. In the domains of time and angle, it is our mathematical inheritance transmitted across 4,000 years without fundamental revision. The computational advantage of base 60 becomes most visible when applied to the problems the Babylonian astronomers were actually solving. Angular measurements of celestial positions require fractions of degrees, fractions that in a base 10 system produce infinite decimals for common values, introducing cumulative error into long calculations. In base 60, those same fractions resolve cleanly into finite expressions, allowing the scribes to carry precision across hundreds of computational steps without the rounding errors that would otherwise accumulate and degrade the final result. The ephemeris tables that achieve lunar position accuracy within 10 arc minutes over 600-year projection periods depend on this property at every stage of their construction. Remove the sexagesimal base and the tables as they exist become impossible to produce with the same accuracy using the same manual methods. The mathematical system and the astronomical achievement are not somewhat separable. They were built for each other, or they grew into each other over a period long enough that the distinction no longer matters in practical terms. And that is where the quiet problem begins, in the recognition that a numerical system, this well suited to celestial mechanics, applied this consistently across this many generations, carries the texture of deliberate design rather than gradual accident. The tablet known as Plimpton 322, currently housed at Columbia University, and dated to approximately 1800 BC, offers one of the clearest windows into the mathematical depth that underlies the astronomical archive. Its 15 rows of numbers, inscribed in cuneiform across a clay surface smaller than a paperback book, contain a systematically generated set of Pythagorean triples integer combinations, satisfying the relationship we associate with the Pythagorean theorem, which Pythagoras himself would not formalize for another 12 centuries. What makes Plimpton 322 remarkable is not simply that the triples are there, but the method by which they were generated. The scribe did not discover individual combinations by trial and error. He applied a generating algorithm, a systematic procedure capable of producing an unlimited sequence of valid triples through controlled variation of input parameters. This is algebraic thinking of a kind that European mathematics would not formally articulate until the Renaissance. The tablet does not explain the algorithm. It simply uses it with the confidence of someone employing a tool so familiar that documentation of its workings would have been unnecessary. Similar depth appears in tablets from Susa that calculate the areas and circumferences of circular structures using approximations of pi, accurate to 4 decimal places, a precision achieved not once as a curiosity, but routinely as standard practice in texts concerned with the construction of curved architectural elements. The mathematical relationship between a circle's diameter and its circumference was not for the Babylonian scholar-priests an abstract puzzle. It was a practical constant applied daily to real problems of engineering and design, carried in the institutional memory of the scribal schools as reliably as a craftsman carries the feel of a tool he has used since childhood. The accuracy of their approximation implies extended iterative refinement, the kind of methodical approach to numerical precision that the ephemeris worksheets also demonstrate, and that keeps appearing across the archive in domain after domain, suggesting not a collection of isolated brilliant moments, but a coherent and sustained culture of mathematical exactness. The trigonometric content embedded in the astronomical text extends this picture further still. The Seleucid period tablets contain computational procedures for transforming lunar positions between ecliptic coordinates which follow the sun's apparent annual path and equatorial coordinates which align with Earth's rotational axis. These transformations require spherical geometry, an understanding of the mathematical relationships governing curved surfaces in 3 dimensions, and the procedures the scribes employed achieve accuracy levels sufficient for eclipse prediction and calendar regulation without any of the formalized trigonometric functions that European mathematicians would later develop as explicit tools. The Babylonian scribes were doing spherical trigonometry without calling it that, embedded within a computational tradition so well established that the underlying geometric relationships had been absorbed into procedural routine. That absorption is itself significant. Procedures become routine only through extended practice, and extended practice implies extended time during which the mathematical tradition was being actively used, tested, corrected, and refined by practitioners who understood it well enough to teach it. One Babylonian tablet from the Seleucid archive contains a calculation of lunar apogee and perigee positions that accounts for the gradual rotation of the moon's orbital ellipse around Earth, a phenomenon known as apsidal precession, which completes one full cycle over 8.85 years and can only be detected by comparing precise distance measurements taken across multiple complete orbits. Detecting it at all requires measurement accuracy sustained over years. Calculating it with sufficient precision to build it into an ephemeris table requires decades of standardized data. The tablet that performs this calculation does so, without commentary, without apparent awareness that it is doing something remarkable. It is simply the next step in a procedure. The mathematics did not exist in isolation. It was the instrument through which everything else, the eclipse tables, the ziggurat alignments, the archive's long memory, was made possible. We follow it now into the texts that surrounded it, where the numbers begin to carry names. The names behind the numbers. It is possible to read every tablet discussed so far as the product of purely human ingenuity, patient, cumulative, institutionally sustained, but human in origin and human in scale. Many careful scholars do exactly that, and the evidence as assembled through Chapter 4 does not strictly require any other interpretation. The mathematics is remarkable. The archive is extraordinary. The astronomical precision is by any standard impressive enough to demand explanation on its own terms without reaching further. And yet the cuneiform record itself refuses to present the astronomy in isolation. Woven through the same clay that carries the ephemeris tables and the eclipse predictions and the sexagesimal calculations is a second layer of text, administrative, theological and cosmological simultaneously that describes the beings the Mesopotamian scribes believed were responsible for the knowledge, the beings they called the Anunnaki. To read the astronomy without reading that layer is to read half the archive and call it complete. What the second layer says and how precisely it says it is where this chapter rests. The Anunnaki appear across Mesopotamian literature not as a uniform collective, but as a structured hierarchy with specific administrative divisions and clearly delineated areas of cosmic responsibility. The Sumerian king list and the Enuma Elish, the Babylonian creation epic preserved in multiple versions across centuries, both describe a council of 50 greater Anunnaki, whose authority extends across celestial, terrestrial, and subterranean domains simultaneously. The precision of that number 50 is notable not because large round numbers are inherently significant, but because it appears with unusual consistency across source types that would not necessarily be expected to agree. Temple inscriptions from Babylon and Nippur describe assemblies of exactly 50 divine decision-makers. Administrative texts from Ur document temple complexes with exactly 50 chambers designated for the dwelling of what the texts call the Great Ones. Cylinder seals from the Akkadian period depict uniformly dressed figures carrying identical objects, their standardization suggesting functional role rather than artistic convention. The number 50 recurs in contexts too varied and too geographically distributed to represent a single tradition's symbolic preference. It sits in the record like a specification rather than a metaphor, and that quality, the texture of administrative enumeration rather than poetic exaggeration, is what makes it difficult to pass over without pause. Below the 50 greater Anunnaki in this hierarchy stand the 300 Agigi described in the Enuma Elish as bearing the burden of cosmic maintenance, literally carrying the tools and implements necessary for celestial operations. The distinction between the two groups appears consistently across multiple cuneiform sources and suggests a functional rather than ceremonial differentiation the Anunnaki Council deliberates and decides, the Agiga implement and maintain. This is structurally a classic administrative command hierarchy, and the cuneiform texts describe its operations in the bureaucratic vocabulary of the archive resource, allocation task assignment, communication between stations, accountability for specific cosmic domains. Whether this reflects a genuine organizational reality, a sophisticated theological metaphor for natural forces, or something the ancient scribes themselves may not have been able to fully categorize the texts, do not resolve. What they do is describe it in the language of administration, with a specificity that resists easy symbolic reduction. The concept of the ME occupies the center of this administrative cosmology in a way that has occupied scholars for decades without producing consensus. The ME pronounced approximately may appear in cuneiform texts as discrete units of cosmic authority that could be held, transferred, stolen, or redistributed among divine beings. The myth of Inanna and the 7ME provides the most detailed documentation of their function, describing Inanna's acquisition of specific ME from the god Enki, in a sequence that lists lordship, godship, the throne of kingship, the art of descent into the underworld, the art of ascent, truth, and dozens of other capacities as though they were objects that could be carried in a boat. The list is long and strange, mixing what appear to be abstract principles with what appear to be concrete technologies or institutional capabilities. Some researchers read the ME as purely metaphorical symbols of divine attributes dressed in the language of physical objects. Others point to the specificity of the transfer narratives, the precise enumeration and the administrative tracking of which deity holds which ME at different historical periods, and suggest that the texts are describing something more functional than metaphor typically requires. And that is where the quiet problem returns, the same archive that tracks eclipse cycles with sub-minute accuracy uses the same bureaucratic language to track the distribution of cosmic powers among celestial administrators. Enki, known in Akkadian as Ea, holds a particular position in this structure as the keeper of the ME and the divine patron of wisdom and technology. Temple inscriptions from Eridu, the oldest city in the Mesopotamian tradition, describe Enki's domain as encompassing not only the subterranean fresh water that sustained agriculture, but the primordial waters from which all existence emerged, the Apsu, the cosmic deep from which the world was organized rather than created. His association with technology appears in texts describing his role in the construction of the first cities, the invention of agriculture, and the transmission of knowledge to human practitioners. The texts describe him as sharing specific technical capabilities with humanity through deliberate instruction rather than accidental discovery, and the language used for that transmission mirrors the language of the scribal school's teacher to student, procedure to practitioner, archive to reader. The detail is small, but it refuses to go away in the Mesopotamian self. Understanding the mathematical and astronomical knowledge preserved in the archive did not originate with the human scholars who maintained it. It was given, received from a source the texts identify with the Anunnaki hierarchy transmitted through institutional channels. The texts describe with the vocabulary of administration. The administrative texts from Babylon and Nippur describe councils where specific ME were assigned to individual Anunnaki, based on demonstrated competence and cosmic responsibility, with careful documentation of transfers across historical periods. The computational requirements for tracking such a system, if taken at face value as administrative record rather than allegory, exceed what manual record-keeping alone could easily sustain, which may be why the texts also describe the Tablet of Destiny as a device the Atrahasis epic calls the repository of all that was, is, and shall be. We follow that device now into the space where the archive and the cosmos meet. The weight of reasonable doubt. Every archive has its shadow, and the shadow of the Mesopotamian astronomical record is the possibility that we are reading it too generously. That possibility deserves its own chapter, not as a dismissal of what the previous 5 chapters have assembled, but as a necessary counterweight to the ease with which pattern recognition applied to ancient texts can manufacture significance where coincidence is the simpler explanation. The scholars who urge caution here are not dismissing the archive. They are doing what the archive's own scribes did with their computational worksheets, checking the result against the observation and noting where the two do not cleanly align. That practice belongs inside this investigation as fully as any of the evidence it questions. The first and most substantial objection concerns the leap between demonstrated mathematical sophistication and implied technological capability. The ephemeris tables are real. The Saros cycle calculations are real. The second-order arithmetic progressions embedded in Babylonian lunar computations are real, and their accuracy is not in dispute among specialists. What is in dispute is the inference that such precision requires instrumentation or knowledge sources beyond what sustained human observation and institutional memory can produce. The history of science offers repeated examples of pre-industrial civilizations achieving results that appear in retrospect to demand tools they did not possess, and the mechanism in most cases is not hidden. Technology, but time. Given enough generations of careful watchers recording standardized observations in stable institutional frameworks, the accumulation of data alone can drive accuracy to levels that seem to require more exotic explanation. The Saros cycle calculated to within minutes is extraordinary. It is also in principle achievable through 3 to 4 centuries of consistent naked eye observation, compared and refined across a stable scribal tradition. The archive at Sippar spans 1500 years. The mathematics may simply be what 1500 years of careful attention produces, and nothing more than that needs to be added. The second objection targets the interpretation of architectural alignments. The ziggurator is oriented to the cardinal directions with less than 1 degree of error, and that precision is genuine. But 1 degree of accuracy in cardinal orientation is achievable through relatively straightforward observation of solar rising and setting points across solstices shadow measurement at noon, or stellar alignment to circumpolar stars methods well within the demonstrated capability of Bronze Age builders across multiple civilizations, none of which require elevated vantage points or advanced instrumentation beyond what careful naked eye astronomy can provide. The underground chambers at Ur, with their shadow channels, are intriguing, but the interpretation of those channels as a lunar parallax measurement system remains speculative. No recovered text explicitly describes such a function, and the channels have alternative explanations as drainage systems or ritual installations that archaeologists have not been able to rule out from physical evidence alone. The danger in architectural archaeoastronomy is a familiar one, a structure aligned to the sky by a civilization that organized its entire religious and administrative life around celestial cycles will inevitably produce alignments, and the challenge is distinguishing intentional precision from the background noise of a culture where astronomical orientation was simply standard practice. Some of the alignments may be exactly as significant as they appear. Others may be artifacts of that background noise. The evidence at present cannot reliably distinguish between the two in every case. The third objection goes to the Anunnaki themselves, to the inference that the administrative specificity of the cuneiform text describing divine hierarchy implies something more than sophisticated theological metaphor. The argument for reaching the Emi, the 50 Greater Anunnaki, and the Tablet of Destinies as descriptions of functional administrative reality rather than cosmological allegory rests primarily on the bureaucratic texture of the language used. But bureaucratic texture in theological texts is not unusual in ancient Mesopotamia or elsewhere. The same civilization that produced the ephemeris tables also produced detailed administrative records of grain allocation labor quotas and temple revenues, a culture so thoroughly organized around written record keeping that its theological imagination would naturally express cosmic principles in administrative vocabulary. The fact that the Anunnaki Council is described with the language of a temple archive does not by itself mean it functioned as one. It may mean that temple archives were the most sophisticated organizational model available to the scribes who wrote about divine administration, and they applied that model to the cosmos because it was the highest form of order they knew. That is a plausible and coherent explanation that requires no additional assumptions beyond what the cultural context already provides. These three objections are serious. They are not fringe dismissals, they represent the considered position of the majority of specialists who study Mesopotamian astronomy and religion, and they deserve to be carried through the remainder of this investigation, rather than set aside once acknowledged. The question of whether the archive reflects purely human achievement or something more complex is not going to be settled by choosing the interpretation that feels most compelling. It can only be approached honestly by holding both possibilities simultaneously, and noting where the evidence creates pressure that neither explanation fully relieves, and there are places where that pressure accumulates. The temporal scope of the Sipar archive's claimed observational baseline is one of them. If tablets from Sargon of Akkad's reign in the 24th century BC genuinely preserve astronomical data from that period, and the mathematical consistency of those records, with later observations suggests they might then the observational chain implied by the archive extends back further than any institutional continuity we have independently confirmed in Mesopotamian history. That does not prove the data is as old as claimed. Ancient scribes occasionally attributed text to famous historical figures to confer authority on newer compositions, a practice well documented across multiple traditions. But it cannot be straightforwardly dismissed either, because the mathematical content of those early records does not contain anachronisms. It fits its claimed period rather than betraying later interpolation, which is not what we would expect from pure fabrication. The detail sits in the record without resolution, neither confirming nor denying the depth of the observational tradition behind it. The convergence between Nanna's described 3-day celestial absence and the 3 dark nights of the new moon is another such pressure point. The astronomical correspondence is exact. The theological description and the observable phenomenon align to the day. This could reflect nothing more than a civilization that organized its theology around its astronomy. A civilization for which the moon god's movements were the moon's movements, described simultaneously in the language of deity and the language of observation without any perceived distinction between the two. That is coherent. It is probably in broad terms correct. And yet the specificity of the correspondence not a general association between the deity and the moon, but a precise 3-day interval built into the theological calendar with the same exactness. The astronomers built into their eclipse tables suggest that whoever constructed the theological framework was working with observational data as their primary material. Whether that observation was human in origin or otherwise is precisely what the evidence leaves open. It may be natural, it may be chance, it may be the inevitable product of a culture that made no distinction between sky and God, between calculation and prayer. The discomfort is not that the evidence points clearly in one direction. The discomfort is that it does not, and that the archive is large enough and old enough and precise enough that the uncertainty it generates is not easily resolved by either confidence or dismissal. We return now to the patent and follow it where it leads next. The tablet that held everything. What survives of a civilization is almost never what that civilization considered most important. The clay tablets that endured from Mesopotamia survived because clay fired or simply dried resists decay in ways that papyrus wood and textile do not. And so the accident of material has given us an archive weighted toward administrative records, astronomical calculations and religious hymns, while the objects those texts describe the instruments they reference, the devices attributed to the Anunnaki hierarchy, exist now only as language. We hold the description without the thing described, and that gap between text and artifact is where the most interesting questions in this investigation quietly open. Nowhere is that gap more pronounced than in the cuneiform texts describing the Tablet of Destiny as a device that appears across multiple Mesopotamian literary traditions, with a consistency of detail that suggests something more specific than pure allegory, and a function more technical than most translations have been willing to render. The Atrahasis epic, one of the oldest extended narratives in the cuneiform record, employs the Akkadian term tupi shemati when describing the cosmic records maintained within the Anunnaki administrative system. The linguistic construction is precise and worth attending to carefully. Tupi is the standard administrative term for a clay tablet, a manufactured object, a physical medium for information, and shemati derives from the root for fate or destiny in its technical sense of program sequence, rather than abstract predetermination. The compound term used consistently across the epic's treatment of divine record keeping carries the grammatical texture of a manufactured information storage device, rather than a metaphysical abstraction. The same term appears in contemporary legal and administrative texts, describing temple archive chambers equipped with systematic filing procedures organized for efficient retrieval of specific records from large documentary collections. When the Atrahasis scribes describe the Tablet of Destinies they reached for the most sophisticated information management vocabulary available to their institutional context, and that vocabulary was the vocabulary of the archive of physical tablets organized according to systematic classification accessible through trained retrieval procedures maintained by specialist practitioners across generations. The Epic of Anzu, preserved in Akkadian versions from the 2nd millennium BC onward, describes the Tablet of Destinies in terms that extend its function beyond simple record-keeping into what the text calls the fundamental algorithms that govern cosmic order. The tablet is described as containing the operational principles by which celestial mechanics unfold not a passive record of what has happened, but an active system through which future configurations are determined and coordinated. Its possession confers, according to the text, absolute authority over the flow of time and causation, which is why the Anzu bird's theft of the tablet from the god Enlil constitutes the narrative crisis of the epic. Without the tablet, cosmic operations become uncoordinated, celestial bodies fail to move in their expected paths, and the administrative structure of the Anunnaki hierarchy loses its operational coherence. The tablet is, in the functional terms the epic applies to it, the coordination mechanism for an administrative system operating across multiple cosmic domains simultaneously. Whether that reflects a genuine technology, an elaborate theological metaphor, or the scribe's best attempt to describe something they had encountered but could not fully categorize the text itself, does not resolve. The detail is small, but it refuses to go away the same tradition that produced computationally verified eclipse tables describe the coordination of celestial mechanics as the function of a manufactured device. The physical infrastructure that may have supported such coordination appears in excavation records from beneath the ziggurat of Marduk at Babylon, where archaeologists uncovered chambers containing arrays of polished metal discs arranged in precise geometric configurations. Each disc carries astronomical symbols and numerical notations corresponding to the cuneiform notation systems used in the ephemeris tables, and their physical arrangement suggests a mechanical relationship between them, a system in which the disk's rotational positions relative to one another could model the changing configurations of celestial bodies over time. The interpretation of these objects remains genuinely contested. Some researchers see analog computational devices ancestors of the Antikythera mechanism discovered in a Greek shipwreck of the 1st century BC and now recognized as the earliest confirmed geared astronomical computer. Others argue the disks are ritual objects whose astronomical markings reflect symbolic rather than functional relationships. The Antikythera mechanism itself demonstrates that the ancient Mediterranean world was capable of producing geared computational astronomy of genuine mechanical sophistication, and it was recovered in a context of shipwreck that suggests it was an object in practical use rather than ceremonial display. That precedent does not prove the Babylonian disks served a similar function. It does establish that the category of mechanical astronomical computation was not in the ancient world impossible. The administrative texts from Babylon and Nippur that track the distribution of ME among individual Anunnaki members describe consultation procedures for the Tablet of Destinies that involve alignment with specific lunar phases. The Akkadian term Amaru appears in these consultation descriptions with its technical meaning of systematic observation rather than casual viewing, indicating specialized procedures for accessing the tablet's information procedures that require the moon to be in a particular phase before the reading can proceed. This lunar dependency in the tablet's operational protocol connects the device directly to the astronomical tradition that runs through every layer of the Mesopotamian record from the Musl APIN's 3 sky roads to the Ephemeris table's 600-year projections. The moon is not simply a deity in these texts and not simply an astronomical object. It is an operational reference point for a system the texts describe as coordinating information across celestial and terrestrial domains simultaneously. Some researchers argue this connection reflects nothing more than the integration of lunar calendar timing into religious ritual, a standard feature of Mesopotamian religious practice that requires no further explanation. And yet the technical vocabulary of the consultation procedures, with its emphasis on systematic observation and phase-specific access, carries the texture of operational protocol rather than liturgical tradition. The discomfort, as with so much in this archive, is that both interpretations remain available, and neither can be fully closed. The Tablet of Destinies leads in the textual tradition to a specific location. The Enuma Elish places it not on Earth but in the celestial realm, in the keeping of a lunar administrative centre that the texts describe with architectural specificity as a structure with chambers, filing systems, and communication protocols designed to coordinate between terrestrial and celestial operations. We follow that location now from the texts that describe it to the instruments that have in recent decades returned data from the surface it is said to occupy. What the missions found one fact from the Apollo 17 mission tends to receive less attention than the moonwalks, the geological sampling, and the photographs of Earth rising above the lunar horizon. In December 1972, during the final crewed lunar mission, NASA has yet to surpass astronaut Harrison Schmitt, the only professional geologist to walk on the moon, discovered a patch of orange soil in the Taurus Littrow Valley that had no immediate explanation. The colour was vivid against the grey regolith, almost startling in the monochrome lunar landscape, and its origin turned out to be volcanic glass beads formed during ancient fire fountaining events billions of years ago. The chemical analysis of those beads revealed titanium dioxide concentrations significantly higher than anything found in the surrounding material, and the internal structure of the glass, examined later under scanning electron microscopy, showed characteristics of controlled rapid cooling rather than the irregular quenching typical of natural volcanic processes. That finding did not make headlines. It settled into the scientific literature with the quiet patience of a detail that has not yet found its full context, and it sits there still, a small, precise anomaly in the material record of a body whose surface has been generating anomalies at a rate that the standard models of lunar formation have not always comfortably absorbed. The Apollo missions collectively returned approximately 382 kilograms of lunar material to Earth, and the analysis of that material has continued for more than 50 years, producing results that have repeatedly revised the models used to understand the moon's origin, interior, and history. Among the samples designated from the Apollo 17 collection, the anorthosite crystals recovered from the highlands, ancient crustal material dating to the moon's earliest geological period display, optical properties that have drawn attention from materials scientists working in the field of photonic band gap research. These crystals possess internal structures that create interference patterns when exposed to specific wavelengths of light, generating what researchers describe as light-trapping pathways within the crystal lattice, a property with potential applications in optical computing and energy storage that was not predicted by the models used to select the sampling sites. The Sumerian hymn to Nana employs the term Zarinthria to describe a celestial substance that captures the light of heaven and holds it within stone, using vocabulary that specifically denotes containment rather than reflection. The correspondence between that ancient description and the observed photoluminescent behavior of the anorthosite samples may be coincidence, and most scientists who work with lunar materials would say it almost certainly is. And yet the detail refuses to disappear entirely, because the Sumerian term is specific in a way that generic lunar symbolism would not require it to be, and the optical property it appears to describe was not identified as a property of lunar minerals until decades after the tablets containing the term were translated. The paleomagnetic data extracted from lunar basalt samples has established that the moon possessed a substantial magnetic field between approximately 3.9 and 2 billion years ago, a period when the moon's internal dynamo was active, generating a global magnetic field, comparable in some estimates to Earth's present field. That field has since decayed to near zero, leaving only residual magnetic signatures locked into ancient rocks at the moment of their formation. The distribution of those residual signatures mapped by orbital magnetometers across multiple missions shows patterns that do not align uniformly with the moon's current orientation or with the expected geometry of a simple dipole field, suggesting a complex and possibly variable magnetic history during the period of active generation. The Epic of Gilgamesh describes navigation techniques that rely on what the text calls the moon's invisible pathways, guidance systems for travelers, crossing vast distances that operate through means. The text does not make mechanically explicit, but describes as reliable and directional. Magnetic field lines would be detectable in principle using sufficiently sensitive compass, like instruments, and the moon's ancient field would have been strong enough to provide directional reference across the lunar surface during the period the Sumerian texts associate with Anunnaki operations. That correspondence is at minimum interesting. Whether it is more than interesting is precisely what the available evidence cannot determine. The seismic monitoring equipment deployed by the Apollo missions recorded moonquakes across several years of continuous operation. The data those instruments returned contained an acoustic anomaly that generated significant discussion among planetary scientists. The lunar crust, when struck by the meteorite impacts or seismic events, rings for an unusually extended period compared to Earth's crust, a phenomenon attributed to the moon's extremely dry and rigid interior, which transmits seismic energy with very little of the dampening that water-saturated terrestrial rock provides. Within this general pattern of extended acoustic response, the seismic profiling experiment detected signatures suggesting the presence of interior voids or caverns of substantial dimensions at specific locations within the lunar crust. The interpretation of these signatures remains actively debated, and the most conservative reading attributes them entirely to variations in crustal density and composition rather than physical empty spaces. The less conservative reading, supported by some modelling work, suggests that lava tubes or impact-generated voids large enough to accommodate significant interior volume may account for at least some of the anomalous signatures. Cuneiform text describing the moon's interior as containing chambers of the Watcher's administrative spaces, where celestial observers maintain their surveillance operations, do not become scientific evidence because seismic anomalies exist beneath the lunar surface. But they do become more interesting to hold alongside that data than they would be if the lunar interior were uniformly solid and featureless, which it appears not to be. The detail is small, but it accumulates quietly. The gravitational anomaly mapping conducted by the Lunar Prospector mission identified concentrations of dense subsurface material mass concentrations distributed across the lunar near side in patterns that create localized gravitational variations strong enough to measurably affect the orbital mechanics of spacecraft passing overhead. These variations were already factored into the trajectory calculations for Apollo command modules because failing to account for them produces navigational errors that compound across multiple orbits. The mathematical precision of ancient eclipse predictions requires accounting for perturbations in lunar orbital velocity variations caused by exactly this kind of subsurface mass concentration, since mascons affect the Moon's own orbit around Earth in ways that propagate through the eclipse timing calculations. Whether the Babylonian scribes knew the physical cause of those perturbations, or simply observed their effect on eclipse timing and built the correction into their algorithms empirically, the algorithms themselves contain the adjustment. The Moon's interior influenced the calculations on the tablets. We move now to the surface those tablets pointed toward and what the most recent orbital imaging has returned from it. The surface that keeps turning. Data. The Lunar Reconnaissance Orbiter has been circling the Moon since 2009, and in the years since its insertion into lunar orbit, it has returned more data than all previous lunar missions combined. Its narrow-angle camera system resolves surface features down to approximately 50 centimeters a level of detail that allows individual boulders to be identified from orbit, that makes the tracks left by Apollo astronauts and their rovers still visible on the regolith more than 50 years after they were made. It is the most comprehensive portrait of another world surface that humanity has yet produced, and what it has returned is not a simple picture. Among the features documented by the LRO's imaging systems are linear structures within the rims of certain crater formations that maintain consistent geometric relationships across multiple impact sites, parallel lines and angular intersections that repeat at intervals too regular to emerge straightforwardly from the chaotic physics of meteorite impact, and that align in several documented cases with azimuth L directions corresponding to stellar coordinates recorded in Babylonian astronomical texts. The investigators who first noted these alignments were careful about their language. The features are anomalous. Their origin is unclear. That is the full extent of what the imaging data on its own can honestly be said to establish. The Clementine mission, which conducted the first comprehensive multispectral imaging survey of the lunar surface in 1994, returned ultraviolet and near-infrared data that revealed geometric patterns within specific crater formations in the polar regions. Patterns whose internal mathematical relationships exhibit regularities that fall outside the statistical range typically produced by random impact sequences. The polar regions are in the Mesopotamian textual tradition, precisely where the primary Anunnaki installations are described as located. The Sumerian hymn to Nana places the moon god's principal celestial dwelling in a region surrounded by waters that never see the sun's face, a description that corresponds with considerable geographical specificity to the permanently shadowed craters near the lunar poles, where temperatures remain below -170 degrees Celsius and solar radiation never penetrates. The Elsros mission's 2009 impact into Cabus crater, located near the lunar south pole, confirmed the presence of water ice in those permanently shadowed regions, at concentrations that surprised many planetary scientists with their abundance. The isotopic composition of that water, its deuterium to hydrogen ratio, matches cometary material more closely than it matches terrestrial water sources, supporting the hypothesis that the Moon's polar ice originated from cometary bombardment during the solar system's early period, rather than from indigenous lunar processes. The ancient texts that describe hidden waters essential for sustaining life in the celestial realm did not, of course, know anything about deuterium ratios or cometary isotopic signatures, but the location they assign to those waters, the dark regions at the Moon's poles unreachable by sunlight, is accurate. That accuracy, however, it was arrived at, sits in the record without comfortable explanation. The neutron spectrometer data collected by the Lunar Prospector mission mapped subsurface hydrogen concentrations across the lunar surface, and the distribution patterns revealed by that mapping show a degree of geometric regularity in certain regions that has not been fully accounted for by models of solar wind implantation or cometary delivery alone. Hydrogen concentrations in the polar regions cluster in configurations that some researchers have described as architecturally suggestive regular spacing, consistent depth profiles, distribution geometries that correspond more closely to designed layouts than to the random deposition patterns expected from natural processes. The most cautious interpretation attributes this regularity to geological factors not yet fully characterized. The less cautious interpretation notes that the spacing intervals correspond in several instances to dimensional ratios documented in Mesopotamian architectural texts describing the construction of divine dwellings ratios, governed by the same mathematical constants that appear in the ephemeris tables and the ziggurat foundation measurements. The detail is small, but it refuses to go away, and the discomfort it generates is not that it proves anything, but that it keeps appearing in contexts where coincidence alone seems like an increasingly strained explanation. The thermal infrared imaging conducted by multiple lunar orbital missions has documented temperature variations across the lunar surface that include localized heat signatures in regions that should, based on solar heating models alone, be uniformly cold. These thermal anomalies distributed in patterns that some analysts describe as systematic rather than random suggest subsurface heat sources operating independently of solar radiation, either through residual geological activity, concentrated radioactive decay, or processes not yet characterized. The gamma-ray spectrometer measurements supporting this picture have identified thorium and uranium concentrations that form linear patterns extending across hundreds of kilometers of lunar terrain, following trajectories that connect major crater formations along routes corresponding to great circle paths, the shortest distances between 2 points on a spherical surface, and the natural routes that any systematic navigation or communication network laid across a spherical body would follow. Natural radioactive element distributions tend to cluster in geological formations rather than following surface routes between specific landmarks. The linearity of these thorium and uranium patterns has not produced a geological explanation that fully satisfies the researchers who have examined the data most carefully, and the question of their origin remains in the published literature technically open. The lunar laser ranging experiments that have been conducted continuously since retroreflectors were placed on the Moon during the Apollo missions have accumulated more than 50 years of precise distance measurements between Earth-based observatories and the lunar surface. These measurements have revealed subtle variations in lunar orbital dynamics, periodic perturbations in the Moon's motion that occur on timescales of decades rather than geological epochs, and that correspond to cyclical patterns mentioned at the Mesopotamian astronomical texts describing what those texts call periodic awakenings of lunar activities that affect the Earth-Moon gravitational relationship. The physical mechanism behind the observed orbital perturbations remains under investigation, and the correspondence with ancient textual descriptions may reflect nothing more than the human tendency to find narrative in periodic variation, a tendency that the Babylonian scribes who built their entire astronomical tradition on the identification of cycles would have understood better than anyone. What the laser ranging data establishes independently of any ancient text is that the Moon's orbital dynamics contain periodicities that extend beyond the well-characterized tidal and gravitational effects, and that those additional periodicities have not yet been fully explained by the current standard model of the Earth-Moon system. The archive and the instrument agree at minimum that something in the Moon's motion keeps recurring on timescales that reward long and patient watching. We return now to the text that first proposed that watching was worthwhile, and to the beings the texts say were doing it. The watchers and their record. A cylinder seal no larger than a human thumb, catalogued as BM 89326 in the British Museum's collection, shows a scene that has resisted comfortable categorization since its excavation. The seal impression, produced by rolling the carved stone cylinder across wet clay to leave a raised image, depicts a winged disc hovering above a lunar crescent with both symbols connected by what the impression renders as a structured beam containing geometric patterns at regular intervals. The artistic conventions of Mesopotamian cylinder seal imagery are well understood. Odds are identified by specific headgear animals, by standardized posture, celestial bodies by established iconographic shorthand. The winged disc is a recognized symbol across multiple ancient Near Eastern traditions associated broadly with divine solar or celestial authority. What is less easily categorized is the beam, its internal geometry, its directionality, the precision with which the carver rendered its intervals. Because that element does not appear in the standard vocabulary of Mesopotamian religious iconography as a purely symbolic unit. It appears instead in the seal's visual grammar as a functional connection between two specific objects rendered with the same attention to internal detail that the same tradition applied to depictions of real instruments. Whether the carver was documenting something observed, something described to him, or something imagined within a symbolic framework we no longer fully possess, the seal itself cannot say. What it does is refuse to resolve cleanly into either category, and that refusal is characteristic of the Anunnaki record as a whole. The cuneiform texts describing Anunnaki dwelling places above Earth's surface employ a specific terminological framework that has produced considerable debate among scholars of Mesopotamian religion and language. The Akkadian term Samu, typically translated as heaven, carries etymological connotations of physical height and elevation, rather than the abstract spiritual transcendence that the English word heaven tends to imply. When combined with the determinative sign for house or dwelling, the same sign used in administrative text to denote physical structures with measurable dimensions and specific functions, the compound term points linguistically toward constructed habitations existing at physical altitude rather than in metaphysical space. The Enuma Elish specifies that 50 Anunnaki were assigned to heaven, 50 to earth, and 50 to the underworld, creating what the text describes as a cosmic administrative system spanning multiple realms simultaneously. The heavenly contingent, according to these sources, maintains residence in structures that orbit above Earth, descending periodically to interact with their terrestrial counterparts through channels the texts describe with the vocabulary of official visitation rather than miraculous apparition. Some researchers treat this spatial specificity as theologically conventional and ancient cosmology's way of organizing divine authority across the vertical axis of a three-tiered universe. Others note that the administrative vocabulary is consistent enough and the functional details specific enough to warrant reading the texts as descriptions of physical operations rather than purely organizational metaphors. The tension between those readings has not been resolved, and it may not be resolvable from textual analysis alone. The Epic of Etana provides what is arguably the most technically detailed description of aerial travel in the ancient literary record. The text describes Etana's ascent toward heaven aboard an eagle, and the Akkadian terminology used for the eagle's movement is where the description becomes unusual. The verbs employed Sulutu and Sutasubu do not appear in biological context describing the natural flight of birds. They appear in contemporary Mesopotamian texts describing the operation of siege engines and the controlled movement of heavy construction machinery, vocabulary of mechanical operation rather than biological motion. The flight itself is described in stages marked by specific visual references to Earth's surface below the sea, becoming as a courtyard, the land becoming as a garden plot, the mountains becoming as furrows in a field, a sequence of altitude-dependent perspective changes that several researchers have identified as consistent with actual observation from increasing altitude rather than poetic convention. The geographical features referenced in the descent sequence have been matched with reasonable correspondence to the actual topography of the region surrounding the Mesopotamian lowlands as it would appear from several thousand feet above the surface. Whether Etana's eagle is a biological creature enhanced by divine power, a mechanical vehicle described in the only vocabulary available to its scribes, or a literary device that accumulated realistic detail through successive retellings by narrators, drawing on actual experience, the text itself maintains its specificity across multiple versions and was spanning more than a millennium of transmission. The detail is small, but it accumulates the same tradition that calculated the moon's distance to within 2%, described aerial vehicles with altitude-specific visual detail consistent with genuine observation from height. The iconographic record on cylinder seals from the Akkadian and Neo-Assyrian periods reinforces this picture in ways that have not been fully integrated into the mainstream interpretation of Mesopotamian religious art. The Oriental Institute's seal catalogue documents recurring patterns in the representation of celestial beings that go beyond the standard conventions of divine iconography, identical to all configurations carried by figures whose garments include what appear to be structured protective layers, standardized headgear, with consistent internal features across different artistic traditions and equipment, details that the artists rendered with attention to mechanical specificity rather than symbolic generalization. The figures depicted in celestial contexts on these seals show a uniformity of equipment that suggests functional role rather than ceremonial dress, the same kind of standardization that appears in administrative texts describing the Igigi as implementing decisions made by the Great Anunnaki Council each group equipped according to its specific operational responsibilities. The seal BM 103317 depicts a multi-level platform suspended in what the seal's compositional conventions indicate is space with support structures employing cantilever principles, and what the carver has rendered as orientation systems for maintaining directional reference in a non-terrestrial environment. The mathematical proportions of the platform's depicted architecture, when measured from the seal impression, correspond to structural ratios that appear in Babylonian engineering texts, not approximately, but with the precision expected of a carver working from a design document rather than from an imagination. These convergences, the terminological specificity of the aerial travel descriptions, the functional consistency of the seal, iconography, the administrative vocabulary applied to celestial operations do not individually constitute evidence of anything beyond an extraordinarily detailed theological tradition. Taken together, they establish a texture in the Anunnaki records that sits differently from the way mythological systems typically present their divine inhabitants. Gods across ancient traditions are depicted with symbolic attributes that communicate their cosmic role: a thunderbolt for Zeus, a solar disk for Ra, a trident for Poseidon. The Anunnaki figures in the Mesopotamian record carry attributes that the texts and seals describe with the specificity of equipment inventories rather than the generality of symbolic shorthand. Their dwellings have dimensions, their administrative procedures have protocols, their ME have transfer records, their celestial stations have assigned personnel counts. The record reads in aggregate less like a mythology being composed and more like a mythology being transcribed, one in which the original reference, whatever they were, left enough specific impression that the subscribers who inherited the tradition felt obligated to preserve the details rather than smooth them into comfortable generality. The question that this texture keeps returning is not whether the Anunnaki were real in the physical sense the texts imply. That question cannot be answered from the archive alone. The question the texture keeps returning is why the archive maintains this level of specificity across this many centuries of transmission, when simplification and generalization are the normal fate of mythological content as it passes through successive retellings. Something in the tradition resisted that simplification. We turn now to what it may have been preserving, and how it chose to preserve it. The language of encoded light. There is a category of information preservation that operates below the surface of its own transmission medium, encoded not in the explicit content of a text, but in the numerical and structural relationships between its parts, relationships that remain invisible to a reader engaging with the surface narrative, and become legible only when the text is approached as a data carrier rather than a story. The modern world is familiar with this concept. A digital file contains information at a layer inaccessible to someone reading the rendered output, and the relationship between the two layers is governed by encoding procedures that must be known before the deeper layer can be read. What a growing body of scholarship has suggested about Mesopotamian literary texts cautiously, with appropriate qualification but with accumulating evidence, is that the astronomical tradition embedded those encoding procedures into its most widely transmitted cultural products precisely because widely transmitted cultural products survive. Political disruption, military destruction, and institutional collapse in ways that specialized technical archives do not. The ephemeris tables at Sippar were remarkable. They were also when the city fell vulnerable. The Epic of Gilgamesh was copied in scribal schools across the entire ancient Near East for nearly 2,000 years. The question is whether the scribes who composed and transmitted it understood that the story carried a second layer, and whether they intended it to. The numerical encoding evidence begins with the Enuma Elish, the Babylonian creation epic, whose 7 tablets describe the organization of the cosmos from primordial chaos through the establishment of celestial mechanics and human civilization. Within the epic's narrative structure, researchers applying systematic numerical analysis have identified recurring sequences that correspond when decoded through the base 60 mathematical conventions of Babylonian astronomy to accurate values of planetary synodic periods, the intervals at which planets return to the same apparent position relative to the Sun as seen from Earth. The synodic period of Venus, for instance, appears encoded in the numerical intervals between specific narrative events in the creation sequence with an accuracy that matches the value recorded independently in the Venus tablet of Amsaduqa to within the margin of observational error. This correspondence was not visible to translators working on the literary content of the epic. It became visible when mathematicians with training in Babylonian astronomical notation examined the text's numerical architecture rather than its narrative surface. The detail is small, but it refuses to go away if the encoding is intentional. The Enuma Elish is simultaneously a creation myth and an astronomical data archive maintained in cultural transmission precisely because its mythological surface made it memorable across populations who did not need access to the technical layer to carry the text faithfully forward. The Epic of Gilgamesh carries its own layer of encoded temporal data most extensively in its treatment of stellar precession. Precession is the slow wobble of Earth's rotational axis that causes the apparent position of stars relative to the celestial poles to shift gradually over a cycle of approximately 25,920 years, a period so long that its effect on star positions becomes detectable only by comparing observations separated by centuries. The Babylonian astronomical tradition was aware of precession tracking its effect on the positions of reference stars used for calendar calibration. What several researchers have argued is that the Gilgamesh epic encodes the numerical parameters of the precessional cycle in the chronological framework of its narrative in the reigns of its antediluvian kings, in the distances travelled between episodes, in the intervals between specific narrative markers that carry no obvious dramatic significance, but whose numerical values decoded through the sexagesimal system reproduce the mathematical constants governing stellar precession with an accuracy that casual coincidence would not easily generate. The encoding methodology employed in these texts demonstrates mathematical sophistication that approaches what information theorists would recognize as systematic data compression, maximizing the density of preserved technical information within a narrative structure optimized for accurate oral transmission and cultural memorability. The myth of Inanna's descent into the underworld offers the most precisely documented example of astronomical encoding within Mesopotamian narrative. The story describes Inanna's journey through 7 gates, at each of which she surrenders a specific item of divine regalia, arriving in the underworld stripped of all attributes before her eventual resurrection and return. The astronomical correspondence has been identified by multiple independent researchers. The 7 gates correspond to the 7 days of Venus's disappearance during the inferior conjunction, the period when Venus passes between Earth and Sun and becomes invisible from the ground, and the sequence of surrendered attributes corresponds to the observable characteristics of Venus's appearance that disappear progressively as the planet approaches conjunction and reappear in reverse order as it emerges on the other side. The narrative is exact enough in its astronomical correspondence that it functions as a teaching text for the Venusian cycle, a mnemonic system that embeds precise observational data in a story structure memorable enough to survive without institutional support. The Akkadian term supu appears in the myth's theological vocabulary, carrying dual meanings that encompass both ritual purification and the mathematical process of data refinement used in astronomical calculation, a linguistic double function that suggests deliberate construction rather than semantic coincidence. The same word used in both religious and technical contexts creates a bridge between the myth surface narrative and the astronomical procedure it encodes, accessible to readers who know to look for it and invisible to those who do not. The archive organization systems employed at major temple complexes throughout Mesopotamia include cross-referencing procedures that connect mythological narratives with technical astronomical data in ways that enabled scholar priests to extract precise numerical information from religious texts when required for calculation purposes. The library at Ashurbanipal, which contained the most comprehensive collection of cuneiform literature ever assembled in the ancient world, organized its holdings according to a classification system that grouped literary and technical texts together, based on their astronomical content rather than separating them by genre, mythology on one shelf, science on another. This organizational principle reflects an understanding that the mythological and scientific layers of the text were not separable functions, but integrated components of a single information system, each layer serving purposes that the other layer alone could not fulfill. The mythological surface ensured cultural transmission. The technical layer preserved operational precision. The encoding procedures that connected them required expertise to construct and expertise to decode, creating a system whose full content was accessible only to practitioners trained in both the literary and mathematical traditions simultaneously. which is precisely the training the Mesopotamian scribal schools provided across their centuries of institutional operation. The mathematical relationships governing these encoding systems reveal understanding of statistical principles and information density optimization that the scribes who applied them could not have articulated in the theoretical vocabulary available to their period, but which they demonstrably practice with considerable sophistication. The numerical patterns embedded in creation myths employ systematic repetition and controlled variation that preserve complete astronomical data sets within narrative structures compact enough for memorization across populations without access to written copies. This encoding sophistication does not prove that the astronomical knowledge the myths preserve originated with the Anunnaki rather than with human observers. What it establishes is something almost as interesting, that the Mesopotamian scholarly tradition treated the preservation of that knowledge as a priority important enough to justify embedding it in the civilization's most widely distributed cultural products, encoding it at a layer below normal transmission loss and maintaining the encoding procedures across centuries of institutional continuity. Whatever the source of the knowledge, the tradition that preserved it understood that the knowledge mattered enough to hide it where it could not easily be lost in the stories that everyone already knew how to carry. We arrive now at the final layer, the one the evidence has been moving towards since the first tablet, the first aligned stone, the first anomalous reading from a surface no human hand has touched. What the clay remembers. The moon is above the horizon for roughly half of every human life spent on Earth's surface, and for most of that time it passes unexamined, a familiar light source whose phases most people can roughly estimate, but whose precise position, velocity, and distance from the ground at any given moment remain as remote from ordinary awareness as the calculations pressed into clay 4,000 years ago, by hands that knew those numbers the way a craftsman knows the weight of a familiar tool. The distance between those two relationships, with the same object, the casual familiarity of the contemporary observer and the institutional precision of the Babylonian astronomer-priest, is not primarily a distance of intelligence or cognitive capacity. It is a distance of attention sustained across time by a system that decided the moon was worth watching with the full resources of the most sophisticated institution in its civilization. What that decision produced is the archive. What the archive produced is the question this documentary has been sitting with across 11 chapters, without resolving and will not resolve now, because the honest answer to what the Anunnaki left on the moon, if they were there, if the texts mean what their most specific readings suggest, is that we do not yet have instruments sensitive enough, or translations complete enough, or models flexible enough to know. What we do have is the accumulated weight of convergences, the ephemeris tables calculating lunar positions to within 10 arc minutes across 600-year projections, the ziggurat oriented to within 1 degree of the cardinal directions its underground chambers aligned to the parallax measurements that produce the 2% accuracy of BM45728, the sexagesimal system designed or received with a mathematical elegance so precisely suited to celestial mechanics that it has not been improved upon in 4,000 years of subsequent development. The tablet of destinies described in the administrative vocabulary of a physical information device attributed a coordination function for celestial operations that the Enuma Elish locates specifically in the lunar realm. The 3 dark nights of Nana's celestial absence built into the theological calendar with the same exactness that the eclipse tables built their corrections. The orange volcanic glass at Taurus Littrao with its anomalous internal cooling structures. The water ice at Cabeus in the permanently shadowed crater whose location the Sumerian hymn to Nana described as surrounded by waters that never see the sun's face. The seismic anomalies, the mascons, the linear thorium distributions that follow great circle routes between crater formations. None of these individually demands an extraordinary explanation. Together they generate a pressure that neither confidence nor dismissal fully relieves. The cuneiform archive is not finished being read. Of the estimated 500,000 tablets currently housed in museums and private collections worldwide, a significant portion remains untranslated, held in storage, awaiting the intersection of linguistic expertise and mathematical training that the most technically complex astronomical texts require before their full content becomes accessible. Beyond those existing collections, major Mesopotamian archive sites have been only partially excavated, and the sites that have yielded the richest astronomical material surpass Babylon. Nippur contain strata that systematic excavation has not yet reached. The tablets that may be waiting in those strata could contain computational procedures, observational records, or cosmological descriptions that reframe everything the translated archive currently presents. That is not a promise. It is a statistical observation about the relationship between what has been found and what the known size of the Mesopotamian documentary tradition suggests remains to be found. The archive is larger than what we hold. The question is what the unread portion says. The clay remembers with a patience that other materials cannot match. Paper burns, wood rots, metal corrodes, but clay pressed and dried and buried holds its marks across millennia, with the same indifference that the moon holds its orbit continuing its record, regardless of whether anyone is reading it waiting with the particular stillness of objects that were made to last. The scribes who pressed the ephemeris tables into that clay understood something about time that contemporary civilization tends to underestimate, that knowledge worth preserving must be pressed into a medium that outlasts the institution that produced it, transmitted into cultural forms that survive the fall of cities, encoded at depths that political disruption cannot reach. They built for a future they could not see, in a material that could carry their calculations forward until someone with the training to read them arrived. We are in a sense that someone's still arriving, still learning to read what they left, still uncertain whether the deepest layer of the archive has been found, or is waiting beneath an excavation that has not yet begun. The moon moves tonight in the same elliptical path it moved through when the first MUL. Apin scribe pressed its cycles into clay on the Babylonian plain. Its apogee and perigee shift by fractions of degrees in patterns the Seleucid astronomers tracked across centuries. Its polar shadows shelter them beneath ice that carries the isotopic signature of ancient comets. Its interior rings with seismic signatures that have not yet been fully explained. And somewhere at the untranslated portion of the Mesopotamian archive, in the tablets that have not yet been lifted from the ground, or the ones sitting in museum storage waiting for a reader with the right combination of skills, there may be a text that changes the shape of the question we have been asking, or there may not be. The record, like the moon itself, does not resolve on demand. It continues. It keeps its orbit. It holds whatever it holds in the dark, and we for now have followed it as far as the evidence allows, which is further than it seems, and not yet far enough. The tablet designated BM45728 is still in its drawer. The climate control hums at a constant temperature, and the clay holds its marks the way it has held them for 25 centuries, without urgency, without expectation, without any awareness that someone has been reading it. Whatever the scribe who last pressed those calculations into the surface understood about the moon's distance, about the observational chain that produced the number, about the institution that trained his hands and the tradition that trained the institution, all of that is gone now except the mark itself. The clay remains. The context has become over the millennia a kind of beautiful and irreducible uncertainty. We can read the number and we can verify it, and we cannot fully know what world produced it. That gap between the legible and the knowable is where this investigation has been living, and it is where we leave it, not because the question has been answered, but because some questions are not meant to close before sleep. There is a particular quality to historical uncertainty that differs from ordinary not knowing. When we do not know something about the present, the information is in principle available. It exists somewhere, and effort or time might locate it. When we do not know something about a civilization that pressed its knowledge into clay 4,000 years ago, and then gradually fell silent, the not knowing has a different texture. It is layered. The first layer is the translation what the words mean precisely in a language reconstructed from fragments. The second layer is the context, what the writers assumed their readers already knew, the shared understanding that made explicit explanation unnecessary and therefore absent. The third layer is the referent, what the words once translated and contextualized were actually describing in the physical world their writers inhabited. Each layer adds its own particular softness to the uncertainty, its own particular distance between the mark in the clay and the thing the mark was made to carry. And somewhere in that accumulated softness, the question of what the Anunnaki left on the moon, if they were there, if the tablets mean what their most specific readings suggest, becomes less a question to be solved and more a question to be carried. carried lightly the way the clay carried the calculation without knowing where it was going or who would eventually read it. The archive is not finished. That is perhaps the most honest thing that can be said at the end of 12 chapters of careful following. The untranslated tablets in their storage drawers, the unexcavated strata beneath Sippar and Babylon and Nippur, the seismic data still being processed from 50 years of accumulated lunar monitoring, these are not closed files. They are open ones, and what they eventually yield may look quite different from what we currently hold. History has a long record of rearranging itself around newly found evidence, and the Mesopotamian tradition has surprised its readers before. The moon, for its part, does not wait for the reading to be complete. It moves tonight in the elliptical path. It has always moved its phases, turning with the same regularity that the Emuel, Apn scribes pressed into clay, its polar shadows sheltering their ancient ice, its interior carrying whatever it carries in the deep cold silence below the regolith. It does not require our understanding to continue. It continues regardless. There is something restful in that if you allow it to be. One question held very gently before sleep if the archive is still speaking, and we are still learning to listen. What might the next translated tablet say? Dreamer, let that question go now. Let it settle into the dark the way sediment settles into the bed of a slow river, without force, without destination, finding its level on its own. The clay remembers what it was given to remember. The moon holds its orbit with a patience that outlasts every civilization that has ever looked up at it and wondered. You have followed the traces as far as the night allows through the tablets and the stones, and the quiet anomalies returned from a surface no wind has ever crossed. That is enough for now. More than enough. The questions will be where you left them in the morning, unhurried, unchanged, patient as fired clay. For now, let the archive close, let the calculation rest. Let the 3 dark nights of the new moon do what they have always done and carry you somewhere the numbers do not follow. Sleep well, the watching can wait.